So my name is Vesey. I'll be teaching this crash course for statistics, and I hope I'll be useful as much as useful as I can because I don't know, you give money, so I want to make it worth it. So I gave money before, and it's kind of worth it, so I was happy. So I want to make it pretty nice experience for you. I know statistics is not the best subject, maybe. I don't enjoy it that much, but we have to pass the exam, so that's the goal. Maybe, I don't know if you need it, but later or any time after the course is finished, you can text me if any, I don't know, question or exercise pops up and you're not sure how to approach it. I'm available and I will try to help it. So, yep. So that's the whole program full of chapters and topics, and I will go through all of them. The only thing I wasn't sure because I was going through the Canvas page that you have, and this week you had chapter 11 and doing some joint probabilities, but I'm not sure if you already take that chapter or you still don't. Can you help me? Do you have your stats lecture this week or it's later, Friday, Thursday?
No, we had one yesterday and the second one was today, but I haven't watched it yet, so I don't know what they covered in this lecture. But
okay, so it's the second part, so maybe tomorrow, I think, in the end of the crash course, I have a few slides, so maybe I can summarize all the information if you haven't watched it yet. So no pressure, not necessary to watch it. So just to start, that's the very first chapter, and I'm just gonna describe some basics, really basics. It's pretty straightforward. So let's start with some definitions. It's not the definitions, but just to find ourselves in the topic. The first case of, we have two events, which are A and B, and we're gonna have a look at their intersection, either their union, complement, and so on. So the first case, maybe you can see my mouse, I'm not sure. Yeah, okay, thank you. A, it's a subset of B, which means that A is smaller than B. So if we have B as one great area, A is somewhere inside. The second case, we have complement of A, which basically means everything but not A. If we have A here, A complement is everything around A but not A. The second one is, maybe that's the hardest part because previously I really got confused between intersection and union because the sign is just upward and downward. So I just take a few notes here. So we can, you can remember the first letter of union is U and the sign is the same as the union. So we have the union of A and B, which means A and B together and everything in A and B. And the second thing is the intersection between A and B, which is basically only the part that is the common part, the part that is in A, the part that is in B. So we are interested in that gray rectangle. Next and last one, we have two separate events. They don't have anything in common. So A is here and B is here. No intersection, no union, no anything. And we don't know if A is larger or smaller than B. We don't know. So some rules. It seems pretty tough, but I hope with the pictures we can manage to somehow understand it. I did my best with paint, so sorry if not clear. I can paint it again or just draw something. The first thing, if we have three events, A, B, and C, and we have to take firstly the intersection between A and B, which would become this part here. Oops. Maybe I can take my pen and just draw. Yep. If we have the intersection between A and B, we will have this part here. And if we take the intersection between A and C, we would have this part here, that is in blue. And if we take the union of those two intersections, it would become this that was red line, but it's already blue, which is part of A, part of B, and part of C. I hope this rule is clear. If anything is not clear or have a question, just stop me, interrupt me. I'll be happy to help. Not just wait the end of the crash course and then hundreds of questions and I will be so confused. So yeah, stop me. The next thing is if we have A and the complement of A and C, and we already know that the complement of A is everything but not A. So we know consequently that A, C, A complement plus A would become the whole sample size, which is the whole sample, which is 1, usually. The second one, if we have the intersection between A and B, and the intersection would be that part here in the middle, and we take just the complement of that blue part, which is everything but not the blue part. So it becomes the red lines, which is equal to the complement of A to the complement of B. Also very simple, but we just have to understand it and not remember it. I think it's better to understand because it's harder to remember so many letters and symbols, and when you have the exercise, it will be so confusing to remember which type of formula you have to use. Nextly, we have a few more complicated ones maybe. And firstly, in that part, we have the intersection between B and C, which is this part here. Okay, I'm gonna try to make my pen a bit, yeah, okay, that blue part. And then we have the union between A and the intersection between those two, which is the blue part. And when we have the union, we have everything, the whole A plus the intersection, which would be equal to the same thing as if we have the intersection between A and B together and A and C together. If you see, that part would be the common one that is in A and is also in the union between A and B and A and C. Nextly, we have, this is more similar to this one. So maybe it would be easier to remember that we have the union between A and B, and then we have everything but not A and B, which is the red lines, which is basically what it says here, the complement of A and B. Nextly, we have 3 events here. So that's a bit complicated maybe. We have A, which is the whole rectangle. Then we have the circle B, and then we have the complement of B, which is the rest of the rectangle. So we have to summarize it. B plus B complement would be equal to A. So A and B intersection, which would be basically B. And we have the intersection between A and B complement, which would be this part with the red lines. And when we sum up this part with this part, it would be just A. So that's pretty, yeah. So let's continue. Do you have any questions about the formulas, or I think the main idea is now to understand everything, not to remember. And in the end, we're gonna solve some exercise and just exercising the formulas. Oops, I have to clear this up. Now we have probabilities, which is basically maybe the easiest part of the course, I think, because the probability of one event is just if we take all outcomes. For example, we have, we're going to an exam, and we can have 1, 2, 3 as a grade, or 5, or 7, or even 8, or 10, for example. But the number of outcomes that I'm going to pass are either above 5.5 or above, yeah, it will be more than 5.5. So we have the number of events that we're going to pass the exam and divide it by the total number of events. And that is just the probability. I'm not allowed to record this one and to send a presentation officially said, but whenever you want, you can take notes and just, I'm gonna waiting for each other to take notes and for the exercise especially. So yeah, let me know if I'm too slow or too fast. I'm gonna wait a bit and yeah, just tell me. Something important, we have to remember that all events, no matter the event, what type of it, in the end, it's always 1. It's sum up always to 1. So the probability of having a 5, the probability of having 8, or so on, all those events, when we sum up them, we're gonna just have 1 in the end. So one little exercise that is pretty straightforward, let's say, if we have a dice which has 6 sides, and we have to calculate the probability of having the event of A when A is having 6 eyes. What do you think? What would be the probability of having 6 eyes when throwing a fair dice? Do you have any suggestion? Yes, thank you for the chat. That's so nice. 1/6, okay. And what do you think if you have to throw a dice but have at most 4 eyes? At most. So not having 5 or not having 6. So we can have 1, 2, 3, and 4, but not 5 and 6. What would be the number? 1/3. Why? Because we just have to take the probability of our event, which is B, having 4 ices at most, which is 1 plus 2 plus 3 plus 4, which is in the end 4 events, divided by the total number of events, which is in the end 4, or in the end 6, sorry. We have total number of events 6, and we are interested in only having those 4 cases. So it will be just 4/6, yeah. Really sorry, yeah, I'm explaining, but it's already the right answer. Yes. So after each topic, before we conclude, I just included a few exam exercises, either taken from your exams on your Canvas page or just my exam last week. And yeah, there are on average maybe 2 or 3 exercises. You can just take notes of them. And in the end of the course, if we have time, I prepared also another 10 or 15 of them, more complicated. So the first one, if we imagine we have the function of x and we have the constant a. It's very important because we have only 3 cases for x. We have either 0, either 1, or either 2. So we don't have a choice. There are only 3 cases. And we have to find a if we know that that function represents a probability model. And the first question, maybe in hint to you, is what do we know about the probability model? What do we know about probabilities? Everything in the end sums up to just 1. So no matter what we do, it has to sum up to 1. So we can just substitute with x in the function and see the results, and then sum up the results and just equal to 1. So for example, if you have, maybe it's easier if we have the table. If we have x as 0, if we substitute x in the formula, you would be having 2 times 0 plus 1, which is just a, 1 time a. If we have x as 1, then we have 2 times 1 plus 1, which would be just 3, and we have 3 times a. And the same for 2. 2 times 2 plus 1, 5, 5 times a. And we know that the probability, the sum of all those 3 events would be equal to 1. And it's nice because we just have 1 a, just 1 unknown, 1 variable, and we just have 9 times a, which is a plus 3a plus 5a, 9 times a. And we have it equals to 1, so it'd be 1/9. Was that hard or was that easy? Can you just orientate me a bit? How is it going?
Yeah, you're a bit fast, so I'm trying to follow.
Oh, okay, so I'm gonna take it slow and just. Yeah. Did you get this exercise, or do you want me to repeat maybe slower?
You can repeat it again.
Okay, sorry.
Thanks.
Okay, thank you. So we have firstly the function, which is a times in brackets 2 times x plus 1. And we know already that x takes only 3 numbers. Is it either 0, is it either 1 or 2? There is no fourth case. and A is a constant. When A is a constant, that means that A doesn't have a number and we have to find it. So the probability model, next step is finding that all probabilities sum up together equal to 1. That is because, for example, the whole sample is just 1. The whole number of probabilities is just 1. And when we take each different case and add it to the previous one, and we take all different cases together, it will be equal to 1. And now becomes maybe the easiest part, just substituting with the numbers in the exercise. We just take x as 0 and we plug it in, and we have 2 times 0 plus 1, which is just 1, which is just a. 1 times a is a. And we have that when x is 0, we have the function equals just a, the constant. And now, instead of 2 variables as it here, we have just 1 variable, which is a. And we just do the same procedure as 1 and 2 for the values of x, of 1 and 2. And when we plug in 1, we have 3 times a. When we plug in 2, we have 5 times a. And that is pretty simple now because we already have just 1 variable. There is no x. We already know that a is a constant, so we have to find it. And we have sum of a plus 3a plus 5 times a, it will become just 9a. And that is just 1. And we have 9a equals 1. We already know that a is just 1 over 9. And when a is 1 over 9, the whole probabilities would be equal to 1, which means that a probability model. Did you get it that way? Is it better, or I should slow it down a bit more? Okay, sure. So second question, if you know that we have x equals 0, 1, or 2, what do you think? What would be the highest profit? In which case of x we would have the highest profit? So the number would be the highest in the end. Is it x equals to 1, to 1, to 0, or to 2? Is it? Yeah, exactly. 5 over 9, but that's, yeah, okay. So that is the last case when we have x equals to 2 and we have 5 times 1 over 9, which is just 5 over 9, which is the table here. So another definition, I'm not sure, there are no particular exercises for that Kolmogorov definition, but I think it's just nice to know the name that is just the same as the probabilities, and there's nothing special about it, just to be familiar with the name. So we have to remember the probabilities and apply all the rules we already know to this type of Kolmogorov function. That is just assigning some numbers, real numbers, to our subset, which is A. And we already know that the probability is in the end always equal to 1. And there is no probability such as -2 or -5, for example, because our event is always, the probability is always between 0 and 1. Why? Because if it's 0, it means that it won't happen. There is 0 chance of happening. But if you have 1, we know that it would happen for sure. And it can be -2, which would be, I don't know. We already know that it can't happen, so it can be worse than that. So there is no such thing as minus something as probabilities. A few more formulas that maybe you're familiar with. The complement, we already told that it minus the probability of A. So the probability of A complement is 1 minus A. That's pretty easy. The next thing is that we have, that is actually one of the formulas we had from the first slide, but I just plugged it in here because we now have an exercise and you can use it not to remember the formula. That exercise, I think it's from my exam last year, if I remember correctly. So it'd be just like a real example. So maybe I can leave you a few minutes just to read the exercise, and if you want to compute it on your own, and of course afterwards I will help and explain the solution. Did you get an answer? Are you stuck somewhere or?
I tried, so.
That's good. That's the start. Did you get A?
0.4 was mine.
Exactly. Yes. Okay. That's true. Then B, did you get
I had 1 as an answer.
Just 1?
Mm-hmm.
Okay. Any other suggestions or? Okay, it's just 1. It's true. And I'm gonna just take the solution right now, but just wanna see. And what is question C?
I had 0.4 again.
0.4. Okay, that's as the first answer, right?
Yeah.
Yeah, point A. Okay. So I hope everyone somehow managed to get those numbers. And I will try to explain now. Firstly, that is pretty straightforward. The complement of AC, which is just minus everything but not A, which is 1 minus the probability of A, which is in the exercise. So we have it 1.4. Then we have the union between A and B, and we just sum up A and B, which are already in the exercise, which is just 1. And now I said it's correct because it's part of the exercise, 0.4, which is your answer as C, which is you get to some point in the exercise, but it's not the very end, but it's somehow nice. So maybe we can start with the probability of B. We have the formula right here. If we just substitute A with B, it will be the same. We have firstly the intersection between A and B, and then the intersection between A complement and B. And now we just have to find those numbers in the exercise and just to substitute them. And if we know already that this thing here is 0.3, the intersection between A and B is 0.3, and B is already 0.4, we already can calculate what is the probability of A complement intersection B. So we just take the formula here. I'm gonna take my pen again. Just 1 second to find it. Okay, so we just take that formula here and try to substitute those numbers, what we already have in that formula. We know that part. it's 0.3. And then we already know B, which is 0.4, which would be, in that case, our B. And 0.4 minus 0.3, it will be just 0.1. Just substituting, just substituting in one formula. I hope the others got it. And continue with random sampling. What is random drawing and what is random sampling? Random drawing is, for example, when you have a bag full of chocolates, for example, and you just put your hand inside without looking, it just takes some random chocolates. It doesn't matter how many chocolates or whatever the bag is, it's just random drawing. If we have random sampling, it means that we have a sample that is randomized. That is the whole sample. I would say that the definitions and the words behind those words, it's not that important. It's better to find your way in the exercises and just to solve them than just to remember some words and you don't know what to expect from. Because when you see in the example random sampling or random drawing, you won't know the formula if you have the words. So just, I suppose, better to solve one exercise and see how it goes, and maybe we can just repeat ourselves later. We have one new formula, which is A conditioned on B. And what does it mean? It means, for example, if we take the exam, what would be the probability of having, for example, an 8, given that we pass the exam? The second event is already given in the exercise, we know it. And we have to calculate the probability of having the probability of A if we know that event B is happening. So it's just the intersection between A and B divided by the probability of B. So if we have the probability of B, we have the probability of C, and we have one condition and one intersection as numbers given in the exercise. Can you calculate the probability of A conditioned B? If you have a look at the formula in the first line, what would be your answer for point A? We just have to substitute that part we already have is 0.3, and probability of B, we already have it, which is 0.4. So it becomes 0.3 divided by 0.4. Maybe I can show the exercise, the whole exercise. Okay, I'm sorry. So is that clear? The formula is just one simple calculation. The second one, we have to think about the intersection between B and C. So we can use the same formula here, which would be, we just have to find this one here instead of this one. So if we just take the intersection between B and C and divide it by the probability of B, we would have the probability of C conditioned B, which we already have. So maybe I will again take my pen and just, yep. I hope you can see it. We already have this one. That's a line. I don't want a line. Okay. So we have to find this one here. But we already know from the exercise those two. We have the conditioned and we have the simple probability. So we just have to multiply 0.4 by 0.2. So it became 0.8. And the next one, we have to find the intersection between A and B. And when we have A and B, the intersection between those two, we just have to multiply the probability of A by the probability of B. Just multiply those two numbers. So if we know the probability of A conditioned B, we would know the probability of A times the probability of B. So we just have to calculate that this probability A intersection B would be divided by the probability of B. So it becomes 0.3 divided by 0.4. So if we know that the probability of intersection A and B equals just the probabilities of A and B, we know that those two events are independent. They're just separate from each other. They don't have any common parts. They don't have intersections. So if we know that, that would be 0.75. We know that those two are independent. So finding the probability of A, and if we know that those two are independent, it's somehow related to each other. It's correlated. So usually after each chapter, maybe I would say maybe we can have a short break of 5 minutes. I'm not sure. We take it pretty fast. We have just 30 minutes ahead. I'm not sure if you need a break. I think we can skip it. But of course, yes, just take a look at the chat. Let me go back to the exercise. Would it be union? Wouldn't C then be a union instead of intersection? Are you talking about the last question? I guess yes.
Yeah, it's the with explanation of C with the probability of A times the probability of B. It says the intersection of A and B, like that the intersection of A and B is same as probability A times probability B, but then wouldn't it be a union instead of an intersection?
Maybe it would be better to if we have the probability of A, that is A, and we have the probability of B. So now if we are looking at the union, which is that sign, A union B, that would be equal to the whole part here, the whole A and B. So maybe that's a bit confusing. But if we have a look at the A intersection B, it would be just the common part. So that part here. So here in the exercise, it says the intersection. So in the intersection, we just have a look at those yellowish part, the small part. And if that part equals to the probability of A times the probability of B, that means we have two independent events. Maybe it's confusing because here they have intersection, but for example, that's A and that's B. Those two are independent events. They happen at different times. They don't have any common parts.
Do they don't have an intersection?
You didn't get the intersection?
If they're both independent?
That's just the formula. It means that when we have A, that's we have the formula for the intersection of those events when they're independent.
Okay. Okay.
When I say two events independent and when I show those two different, they don't have any common parts, that's just for visualization. It doesn't mean like the formula is to calculate the final probability of intersection between A and B. Did it become better or like the point is it?
Yeah.
Okay. In the end, I have a few more exercises about independence, so maybe there would be, yeah, again, useful to go over that topic. So the second part of our today's lecture would be conditional probabilities, and those would be about some ordering some objects in either with replacement, order, or unordered. It doesn't matter. There are different formulas, so we have to remember which case of which probabilities corresponds to which formula. So now those are just the formulas. Now we're going to explain each one of them slowly and with an example and with a calculation example separately. So let's first maybe the basic one, we just have to order k objects. We don't choose from any other object. We just order those given objects. So if we go, for example, to the supermarket and we know your shopping list, we know we have to buy those 5 things. And we have to calculate what is the nth number of paths you can go to the supermarket in order to collect those 5 products. So, for example, you can't go for milk and then for milk again. You have to go for each product once. We just have to buy 1 milk, 1 bread, and so etc. So, for example, I think it would be easier for visualization if we take 5 different boxes. And for example, when you go to the supermarket, the first store that you have to go to is the first position. So for example, when we have to take 5 products from the supermarket, in the first position, we'll have 5 options. We can go for milk, we can go for butter, bread, and so on. So for example, we already took the milk, the first product. We go to the second product. Now we already have 4 products to buy, 4 that are left. We already have the milk, so we have to collect the bread, butter, and the cheese and the chocolate. So here we have 4 options. For example, we now took the chocolate, for example, and now we will have 3 items left to collect. So in that position, we will have 3 options. And it is the same, we already took one. For example, we took the cheese, and now we will have 2 options. For example, we took here the butter, and in the end, it will be just 1 product left that we have to collect. And if we multiply those numbers, in the end, it would be equal to 120 paths. I'm sorry for the typo here. There should be 1 0 here. It is 120 different options to go to the supermarket and collect those products. Based on the fact that we have to collect just 1 butter, 1 bread, and so on. We have to collect them once, and that's enough. The basic formula for when you have those type of exercises is just using factorial, which is just the number of products we already have. For example, k factorial is equal if we k equals to 5 here, it would just become 5 times 4, which is 5 minus 1, times 5 minus 2, which is 3, and so on when we go to 1. So maybe, do you feel comfortable calculating those factorials? Do you need some exercise for those? Or it's a bit hard to get used to the factorial?
An exercise would be nice.
Would be nice. Okay. So, can you just calculate, for example, 7 factorial? What number would you get? Yep, 5040. I'm not sure if you meant exercise just calculating or just a real exercise with the whole situation going on. but now we're going to have a few calculations, and then the next slide we're going to have an exercise. So the next case of counting would be just to have, just we have to choose from a few objects. For example, your mother said to you, you're going to buy either butter, either milk, or either chocolate, and you have to choose one product. That's the case of the second ordering. We have a defined number of possibilities to choose those objects from another object. So it means that we have two cases. We can either replace, for example, we can take those two, we can take milk, butter, and chocolate, or we can't take them, we can just take one product, not all three of them. That's the main difference between this part here, ordered with replacements, and ordered without replacements. So if you take the same example, we just have to buy them, and we would have 5 products for the first probability. We would just have 5 options for here. We would have 5 options for here, and 5, and 5, and 5. So it would become 5 to the power of 5. That's the number of possibilities. And the next case would be, for example, if we take just one. So for example, here there are no products, but just people. So we have a competition, and we have to order first, second, and third place. We have to do the ranking. And if we know that we have to choose from 10 participants, the total number of participants is 10, and we have to choose one for first place, one for second, and one for third. There is no chance of having 2 winners, for example, or 2 people on second place. So the first place here, in the first place, if we have 10 participants, we would have 10 options to choose from for the winner. For the second position, we already chose one person for the winner, so we have 9 options. In the third position, in the third place, we have to choose from 8 people because we already have a winner and we have the second place. So it means it will become just 10 times 9 times 8. That's the easiest way to calculate it. But in your slide, you have a formula that maybe it would be useful if we have, for example, huge numbers that we can just calculate in such a way. And the formula is here. We have m over k in brackets, which would mean m factorial divided by k factorial divided by the difference of those two. And if we take the example with the participants, we have m, which is equal to 10 because we have 10 participants. And then we have k, which is equal to 3 because we have to choose for first, second, and third place. We have to do the ranking for the first 3 places. It doesn't matter the rest of the place what they're gonna rank. So we just substitute here, and we will have 10 factorial divided by 3 factorial, just following the formula, multiplied by 10 minus 3 factorial. And if we calculate this number, it will be the same as this here. So maybe that way of calculating would be easier to understand how, but for big numbers, it will be easier just to use the formula. Was that clear? Those 3 types of counting different things, either with replacement, either without replacement, and we have ordered or unordered. Maybe you can have a few notes of those formulas because we're gonna have them if you haven't too. Do you want me to wait for a second to have a note? Okay, I can continue maybe if I can't see anything from the chat yet. This type of probability is almost the same as the previous one, but it's easy. It's not easy. It's hard to remember into difference between this type and this type because we are already calculating the same way. We are just having we have to choose two people for the same position. It's, for example, we have to choose two people for the winner position. We have to take two people for the first place. I'm sorry for repeating 10 times myself. In that case, we have to choose one winner, one person for the second position, and one for the third. But here we have to choose from a certain number of participants, just two people for the same position. And that would be just 5/2. Here, that's also an exam related question. Do you want me to, maybe we can read it together and just maybe give you some hints? Maybe I can leave you to maybe try to answer the question. Maybe I can go backwards if you want to have a look at the formula, but that's later. So if we imagine we have 4 digits that are part of a code. And we know that that code is consisting only of numbers from 0 to 9, all numbers. So we have to find all codes that can be that could be made if we know that they have to have just 4 and 4, just 2 4s in them. So we have 4 digits, and we know that in those 2 digits we have to have 4s. That's the first case. If we take the boxes as an easier way to calculate, can you imagine for the first position how many options you would have for a number?
Nine, maybe?
9. But remember, we have from 0 to 9, which is 10.
Oh, yeah, 10.
Yeah, 10. And if we take for the second position, again 10, and again 10, and again 10, we will have the total number of those codes. But we have a requirement of having 2 4s. So we have to separate 2 positions from the whole code and just put 2 4s in those 2 positions. So in the first position, let's, for example, say that in the first position we would have 4. So that means we have, if it's 1 4, we have just one number, which is just one option. And if we take the second position as having 4 there, it will be again one option. But for the rest 2 of the boxes, would have all the rest of the numbers. So which is everything, which are 4 in total, without 4, which would be just 9, as you said. Just 9 and just 9. But here we defined the first and the second position for 4s only. But it doesn't say if they should be in the first, in third, in the fourth position. So we just have to adjust. So we have 2 4s here, but we can have 1 4 here, we can have 1 4 here, or just 1 4 here, 1 4 here. So we just have to calculate the probabilities of having those 2 4s around. Do you have an idea how to calculate those? So we already calculated, we have 81 probabilities here. Do you have an idea using those formulas here? If you use those formulas here, which one would you choose to calculate those 4s around? Or do you think that this formula here would be nice to use? Because we have 2 fours if we adapt our example, our exercise, and we have 4 positions in which they could go for. So we just have 4 over 2. That is only for the fours. And if we calculate this, it would be equal to 6. That is, which equals 4 factorial divided by 2 factorial divided by 4 minus 2 factorial. Do you want me to calculate this part, or is it clear that equals to 6?
It's clear for me.
Okay, great. So in the end, we have 81 probabilities and 6, and we just have to multiply 81 by 6, which, if I'm not wrong, should be equal to 4.6, 486, sorry. That is the end answer for part A. And maybe point B is a bit easier because we are not obliged to use any numbers. We just have to have 4 different digits. That's the same as the first example with the milk, butter, chocolate, etc. Do you have an idea how to calculate the number of codes that we have 4 different digits?
Ten, 9, 8, 7.
Yeah, exactly. Okay. So we would have 10 times 9 times 8 times 7, right? That's the total number of probabilities. But here they say define the probability. So if we have the probability, then we have to divide our outcomes that we are satisfied, which are having 4 different digits, divided by the total number of outcomes. So the total number of outcomes is 10 times 9 times 8 times 7. But in our case, we would have 4 different digits. I'm sorry, this thing, I just made a mistake. That is having 4 different digits. And this number, we have to divide it by the total number of outcomes. And the total number of outcomes is having everything. It doesn't matter if they're different, if they're 4s, 5s, etc. We'll have just 10 options for the first position, 10 options for the second, for the third, the same, and the fourth option, again, 10 options. That is the case we are interested in. We're having 4 different digits, and we have to divide by the total number of probabilities, total number of outcomes. And that would be equal to the probability that we are searching for. For example, A. If the event A equals to having 4 different digits. Was it clear, or do you have maybe question? I just want to keep the answers. And if I'm not wrong, here the right answer should be 0 if you calculate the one thing that I showed you, 5040. That is just 10 to the power of 4. And these things that Julie already told us, times 7. If you have questions, you can maybe send me an email or text me, whatever you prefer, and maybe we can go through the same exercise tomorrow if you didn't understand something or I didn't explain something in a clear way, which is totally So just I have to clear these things and continue. In the next example, we would have students as participants, and we know that we have in total, we have 20 of those, 20 students. But there is a separation between first year and second year. So those that are first year are 12, and those that are second are 8. And we know that we have to select some students for presentations, and we have to randomly select them. We have to suppose that each presentation is done by one student only and is done on different times. So one presentation is given maximum by one student. So we have to find the probability that all presentations are given by only first year students. What would that mean? It would mean that second year students are not part of the equation. We just have to we have to concentrate only on the first years. Maybe I should have waited a bit just to read the exercise and then going through the numbers. Do you want a minute to try yourself?
Yes.
Yeah, sure. Okay. If I may help, point A is the same as the part that was asking for the digits, having 4 different digits. The first part will have all cases that we are interested in. For example, having only first year students divided by the total number. What would be the total number? That would be easier to calculate. The total number of probabilities would be just having first year and second year. So it would be 20 times 19 times 18 times 17 and times 16. We'll have 1, 4, 3, 4, 5 presentations. That is the total number. You have to divide our case, our situation by first year students by the total number. So this one would be here. if we imagine the same boxes that we have, for example, we have five places, and we have to fill in those first year students in those 5 places. So we just would have 12 because we have 12 students we can choose from for the first position. Then for the second position, we would have 11 because we already chose one for the first place. Then we would have 10. Then we would have 9 and 8. Those are the cases that we are interested in. Those are only first year students, only first year. And below, they're mixed second and first year. So if we calculate this huge number, but this huge number, in the end, it would be our answer. Did someone got that answer, or a similar one, or a different one? At least, did you get the logic behind?
Yes, I understand.
Okay. At least the logic is there. So if I calculate it correctly, it should be 0.05. If you want to exercise later on the same exercise, that will be the right answer in the end. If we imagine we have a second case, and we have to choose 4 presentations that are given by first years and just 1 presentation given by second year. And also here, we're not asking for the probability, which is our event divided by the number of outcomes. It's just the number of schedules, different schedules. So that'd be just the first part. If we again have those, maybe I can use. So we have those 5 positions as presentations, and we have to fill in them in such a way that we have only 4 first years, not 5. Here we had 5. I would like to give you a minute or two to think about it and just calculate it. And let's see if someone gets the answer, hopefully. Did you get an answer, girls? Okay. Do you want me to wait a few more minutes just to finish the attempt and then What is your answer, Fatih? It has to start with 4. That's not the right answer, but maybe let's try together. We have the same 5 boxes, 5 presentations. And let's start with the first years. We have 12 opportunities to choose from for first year. So we will have 20 students for the first position, 11 students for the second, then we will have 10, and then we will have 9. That is only first year. And for the second years, we have just 1 position. So there are basically 8 students, which is we have to choose from 8 students, which would become that is only second year. But something we have to consider is that it's not necessarily the second years have to be last. They can be first, they can be in between, it doesn't matter. So in total, we have 5 positions, so they can be in 5 positions. So we just have to multiply them by 5. And in the end, we would have 12 times 11 times 10 times 9, that is for first years, and then times 8 for second year, because we have only 8 second year students, and in the end by 5 because of the different, it says different schedules. And in the end, we should get to 475,000. 475,200. That is the number of schedules. If the question was not how many different schedules, but determine the probability having 4 presentations by first year and 1 by second, what would be the solution? It would be just having this number, that is the events that we are asked to, we are interested in, divided by the total number that we already have here, which is the total number of students, which is 20 times 19 times 18, 17, and 16. So the number here, the first number, is always the number of schedules, of paths, of ordering. It doesn't matter. But when we divide by the total number, it's a probability. And the probability is always between 0 and 1. So if we got the probability, for example, previously very often I got probabilities of 10, of 12, of 100, and that was a sign that I'm not having the probability, but I'm having the number of orderings. So if you get number different than 0 point something, maybe that's the number of orderings. I'm not sure if that was a bit tiring. Do you want a having 5 minutes break now? Because we're already 1 hour in. Okay, so maybe we can have 5 minutes. Did you have lunch? Do you need more time to eat, or it's fine?
5 minutes is fine.
Okay, yeah, let's have 5 minutes, and then we're gonna continue with a few more exercises. Ariel here. Fatih, Muriel, Evelina is here. Yes, great. Only Muriel had to join, but I think it's fine because we have another exercise. So we're gonna spend some more time there. So the next one, let me clear my drawing. The next one is again probabilities. So here we have 60 participants in total. And there are 3 questions that need to be answered by those 60 students in total. And we have to calculate in 3 different cases what would be the different orderings of those students answering the questions. Do you want to have maybe 3 to 5 minutes just to read the exercise and try to solve it on your own? And then we're gonna compare answers and explain. Did you do the first case, the first point A? Great. Do you have an idea how to solve it, Julie?
I tried. I did 60 times 60 times 60.
Yep, that's correct. Yep. Okay, I guess everyone has the same, hopefully. So we can try, and if it means donations, is it because, yes, okay, great. We just have 3 questions that needs to be answered. It doesn't matter if they're different people, the order, it doesn't matter. You just put the total number of participants, the students in that case, and just multiply them. In the second case, we have the condition that each student must answer at most once. So we have 3 different people answering those 3 different questions. Did you finish solving this one? It just is the same as question A, but we have to multiply each time. The next number becomes with -1. The first number, we have 60 possibilities for the first question. Already one student here answered. So the second position, we have 59 because that person that answered the first question is not, it's not possible to answer the second question as well. For the third position, 2 people answered, so it became 58. And in the end, we just have to multiply those numbers. I took note. I don't have the right, I mean the end answer, but it should be just 60 times 59 times 8, which would be equal to 205.
Sorry, you mean for the first one, for the first question?
That is for that point.
The first one is what? What did you say the first answer?
The first one is 60 to the power of 3.
Okay, yeah, okay.
Times 6, yeah. The answer to the second one is this one. That is 5. Was that clear? Are you calculating the last question? Did you get a number for it?
For the last, I did the answer of the second one, multiplied it with 3.
Multiplied it by 3.
Yeah.
Because of the number of positions we can change because of the
order.
Yeah. I would say yes, but we can use the formula that was a few slides before. If you remember, it was the number of students, which is 60, which was, forget it. It was m in the formula, and above and below we will have the number of questions that needs to be answered. If you remember with the factorial calculation. And in our case, we have 60 students in total, and we have 3 questions. So that is the quicker and the easiest way not to confuse them. And if you want to calculate this number, it would be 60 factorial divided by factorial of 3 divide times 60 minus 3. I'm sorry for the handwriting. I hope you can see what I 3 times 57 factorial. That would be the end calculation. I hope you wrote it down. Can we continue? Okay, great. So let's clear all my drawing and go to the next slide. There we would have conditional probabilities. Okay, those are the numbers. In the next exercise, we would have again questions, but we have to think about the answers. And we would have 20 different questions, and each question have only 4 possibilities with 1 correct. So we have to calculate if you're taking this test with 20 multiple choice questions with options A, B, C, or D, just 1 correct. And we have to see how many different answer sheets can we have with those questions. That's the same as the first question here. Let me see if that is 4 to the power of 20. It's correct. Great. So we just have 20 positions, 20 of those. For example, I want draw 20, but yes. And in each one of them, we have 4 possibilities to answer. It doesn't say which answer is correct. It doesn't say how many B's, A, etc. We just have to calculate the total number of answers. So we have 4 possibilities because A, B, C, and D for each question. So it will be 4 times 4 times 4 and so on. And those would be 20 positions because we have 20 questions. And in the end, it will be equal to 4 to the power of 20. And nextly, we'll have one more exercise, just calculating those. We just have numbers, and we have to calculate the end result. Just practicing factorials. I will try to calculate them together with you. Do you have an answer maybe for the first one? Did someone got the first one? Okay. 20, yeah, that's correct. Great. The second one, maybe I can just sketch it up to, I'm not sure if others. That's right. Okay. That's good to hear some answers from different people. And the last one. It should be 5. Yeah, that's right. Do you have a question about those? Do you want to calculate them together? Or we can go to the next slide.
Yeah, we can continue.
Okay, great. So now we would have conditional probabilities. I'm sorry. Yep. A few slides ahead. And bias rule, which would be the new one for that presentation. Firstly, I already told you that when we have two probabilities and when they're conditioned, one of them depends on the other. It means, for example, next year profit, given that there are no COVID restrictions. We have already one event that is given. We know it happens for sure, which is COVID restrictions. And then the one event that we are interested in, our profit. So the formula for the conditioned event is the intersection between A and B divided by the probability of B. That is the easiest and the most frequently used formula in our exercise until now. So we already have a few exercises with that formula, the complement of AC, which is equal 1 minus the probability of A. I hope that's clear. And then we will have the complement of A given that B. That would be the same as the previous formula here, where 1 minus the probability of A, but we already have the given B is happening. So it's the same, but just at the B given. We have the second event now, not just the first one. Another useful formula that we have to use, is the union between A and C. In the union between A and C, I'm going to sketch it because it's really easy to see how it goes. We have A and we have C. And we have to calculate the union of those. The union, it means that whole part. It's everything. And we can easily calculate it as summing up the probability of A plus the probability of C. But if we sum up them, we'll have one part that is doubled. We have this small part red that we counted it 2 times. So we just have to minus the intersection, which is here. And in that way, we would have the union between A and C. That formula is already repeated here. I hope it's clear. We just have this one equals probability of B times probability of A given B. So the next one is the bias rule. And we would have the probability of A given B. Remember, we have already one formula for A given B, but this time we would have the probability of A, not the probability of B as it is here. So we would have a connection between A given B and connection between B given A. So we can easily calculate those two if we have the probability of A and the probability of B. So from that slide, I would say just remember that formula and that formula. Everything else you can just find by substituting the numbers and the probabilities. And of course, this formula we already know. So those three are the most important. I will wait for a second to have a note and then continue. I hope you're ready. So now we'll have a look at the table and we're given a few probabilities. And we have to decide on which one we're gonna need to calculate the probability of A given B. Can you guess, not guess, but decide how we're gonna solve the probability of A given B? If we know that B is given, we have to concentrate on this column only. And we have to find the probability of A given B, which means we have to concentrate on A, which is that part here. And when we have a look, the only part that is common is 1.4. That is the probability of having A and B together. And the formula of probability of A given B is the intersection between A and B divided by the probability of B. And the common part, the intersection, is 1.4. And the probability of B would be equal just the sum of those two numbers, the whole column of B. If there was another row here, we have to sum up all those three numbers. Everything that is under B is the whole probability of B, which in that case is 0.5. So in the end, that should be equal to 0.8 as an answer. Do you want to try and give it a try with the second, B given A? That's the same method. Maybe I won't confuse you. I would delete, not delete this, but delete this one. What would be the answer for B given A? When you're ready, you can type it in the chat so I can know you're ready. 1.57. That's correct. And what numbers are those? We have to have a look at 0.4 because that's also the intersection, and the probability of A, which is just summing up those two. 0.4 plus 0.3, which is equal to 0.7. So it would be 0.4 divided by 0.7, which is 0.57. And just one more example, what would be the probability of having A complement given that B? Yep. 0.2. If we have to again calculate it, that just would be, I'll write it here, the probability of intersection between those two, which is this one, 0.1, divided by the probability of B, which is the whole column behind B, which is 0.5. Okay, so I'm gonna clear everything, or just that part that is, and continue. We would have another exercise, which is a poll, and we have to, in the end, we have to know the probability. We are searching for, we have the population, and we know that 80% of the whole populations are said to be football fans. If we have to get randomly two people, and we have to calculate two probabilities. Firstly, having one fan and one person that is not a fan, and the second one that we have two fans. We have to randomly pick from those population of Tilburg that we know 80% of them are fans, and calculate those two probabilities. Just take a minute to read the exercise. I'm not going to confuse you because I think when I read the exercise, I'm just making it harder for you to understand. If you have an idea, type in the chat your answer, or just unmute yourself and did you get an answer?
Can you maybe explain this one? Because I got the part of the fence is 0.8 and the non-fence are 0.2. But that was
That's exactly what we need now. Okay, so if we're already on the same page, the probability of having a fan from that population is 0.8 and not a fan is 1 minus 0.8. That should be clear. Yeah. Then we can just fill in those positions. First case, we have one fan and one non-fan. So the first thing we have to think about having a fan which is 0.8. We just fill it in. And for the second position, having non-fan, which is 0.2. And we just multiply them. That should be equal to 0.16, if I'm not wrong. Yes. Second case, they're asking us for having both fans. So the first place should be a fan, which is the probability 0.8. And the second place should be also a fan. So we have again 0.8. And that is the end answer, which is 0.64. Hope you took notes. And then one more exercise, and that is going to be the last for that topic. So, yep. So we have a partition here, and maybe I should explain what is a partition. Based on the second exercise, we have fans and not fans, and those two groups of people form a partition. A partition is the whole set, the whole sample. And we know that D1, that should be D2, I'm sorry, and D3, the whole thing is just one group of people. They're just separated. So we know that D1, D2, and D3 are partition. We also know that A given D1 is 0.7. And we have to calculate, we are given also all probabilities of A given D1, D2, and D3. We also have the probability as D1 and D2. But we have to find now the whole probability of A that consists of D1, D2, and D3. What would be your suggestion? If we know that, this part, and we can just separate. For example, this is D1, this is D2, and this is D3. And they form a partition. And for example, we have event A, which is here, and that is D. And we are given all those three small areas, A given D, A given D2, A given D3. We have them here. And we just have to calculate the probability of having A. Just 2 minutes to calculate and think about it if you want, maybe a minute even. I'm gonna give you one formula that could be useful. Do you feel ready? It's fine if you don't have a final answer. Do you have an idea just how to start? Okay, let's start from the basics. We know that those three form a partition, which means they equal to 1. And we already have D1 and D2, so we can easily find D3, which is how much? Is 1 minus those 2, which would be 0.1. That's the easiest step to start it. Then we have to use that formula here. We have the probability of A given D1 equals to the intersection between those divided by the probability of D1. We already have D1, which is given by the exercise, and we have this one. So we just have to find the probability of A intersection D1. And we should find all those three intersections, all those three small areas. We can find easily the probability of A. So I will start with the first one. A given D1 equals 0.7